Hello and welcome back. Kamal here, and today we're going to be solving the Malmsten integral, which is just this absolute monster of an integral characterized by a parameter alpha. So we're calling it the integral function I of alpha. And this thing is awesome, man. The first time I solved it, I died, but luckily I survived, which is why I'm recording this solution development. So just comment something when you're done watching the video. Just comment anything to let us know that you survived as well. And this thing is ridiculously awesome because there is so much cool math that goes into the solution development, so many really cool tools and tricks we're going to apply here, and this is absolutely amazing. Enough talking, let's get to solving. The first thing we should notice is that we're integrating from 1 to infinity. We have a log x, and we also have a quadratic polynomial in x in the denominator. So we could benefit from a substitution that is letting x here equal to 1 by u, which implies that dx equals negative 1 by u squared du. That means the target integral I is now the integral from as x approaches 1, we have u approaching 1, but as x approaches infinity, we have u approaching 0, of log 1 by u divided by 1 by u squared plus 2 cosine alpha divided by u plus 1 times negative 1 by u squared du. And of course we can simplify this a bit because in the denominator, well, we have 1 plus 2u cosine alpha plus u squared all divided by u squared. We have this negative 1 by u squared term. And in the numerator, we have log 1 by u. Just wanted to write that to make sure that we don't have a headless integrand or something like that. So we have some nice cancellation, and we can get rid of the negative sign as well by switching up the limits of integration. So we have the integral from 0 to 1 of log. Now, log 1 by u is, of course, negative log u, and we have u squared plus 2u cosine alpha plus 1 du. Okay, cool. And of course, u is just a dummy variable, so I might as well rename it back to x. So we have I of alpha equal to the integral from 0 to 1 of log negative log x divided by x squared plus 2x cosine alpha plus 1 dx. We now shift our focus completely towards the denominator because something really cool is happening here. The cosine function has this really cool expansion, this cool definition in the complex realm, that is cosine alpha equal to e to the I alpha plus e to the negative I alpha divided by 2. So we have x squared plus 2x cosine alpha plus 1 equal to x squared. Now, because we have 2 cosine alpha, that means we have x times the sum of exponentials. So we have e to the I alpha plus e to the negative I alpha plus 1. And you can write this as a product of factors quite nicely. We do need a 1, so we have 1 times 1. And for the x squared terms, x times e to the I alpha times x times e to the negative I alpha works quite well because the product of these two exponential functions is, of course, equal to 1. So plus sign here, plus sign there, and we've recovered all terms, including the cross term, which is extremely nice. So we have 1 by x squared plus 2x cosine alpha plus 1 equal to 1 by 1 plus x times e to the I alpha times 1 by 1 plus x times e to the negative I alpha, which is absolutely beautiful because now we can invoke the geometric series. Recall that we can expand 1 by 1 plus z as the sum over the non-negative integers k of negative 1 to the k times z to the k, provided the absolute value of z is less than 1. And here we have absolute value x times e to the I alpha equal to absolute value x times e to the negative I alpha, both being less than 1 because we're integrating from 0 to 1. So the absolute value of x is indeed less than 1, and the absolute value of both these exponentials is, of course, equal to 1. So we can invoke the geometric series here. So we have 1 by 1 plus x e to the I alpha times 1 by 1 plus x e to the negative I alpha. And I'm going to write this in the expanded form because we'll need that. So first we have 1 minus x e to the I alpha plus x squared e to the 2I alpha minus x cubed e to the 3I alpha, and so on and so forth. And here we have 1 minus x e to the negative I alpha plus x squared e to the minus 2I alpha minus x cubed e to the negative 3I alpha, and so on and so forth. And now I'd like to expand this product. So first and foremost, we do have a 1, which is quite nice. Then we have some x terms. So how do we get the x terms? Well, we get an x term when this thing multiplies with the 1, and we also get an x term when this thing multiplies with the other 1. So that means we have a couple minus signs, so negative x factored out, e to the I alpha plus e to the negative I alpha. Now, what about x squared? Well, we do get x squared when this thing multiplies by 1, and this thing multiplies by the other one. So we have plus x squared. We have e to the 2I alpha and e to the negative 2I alpha, but it's not just done yet, because we can also get an x squared term when these two multiply out as well, which gives us x squared times 1. Okay, cool. So we have a plus 1 here. Now what about x cubed? So for x cubed, again, we do have e to the 3I alpha, and we have e to the negative 3I alpha, but we also get x cubed when this square multiplies by this linear term in x, and we get a negative sign already factored out. So that means we're left with e to the I alpha, and we'll also have e to the negative I alpha, and so on and so forth. And this is actually really cool because we have a nice pattern. That is, we can write this as the sum over, let's call the index variable n now. So we have the sum from 0 to infinity of negative 1 to the n. That takes care of the alternating plus and minus signs we have. And we do have x to the n terms, but they have coefficients a sub n that look very weird, so that definitely attracts us to investigate the weirdness, and oftentimes the weirdness is actually quite beautiful, as it is here. So a sub n, let's see what you look like. Well, we notice here that the first term, well, the second term is in fact the first term with the argument shifted back by 2 units. I hope what I'm saying is making sense. You guys get it in the context of what of what we're solving, or the shapes and structures in front of us. Yeah, it does look like the second term is the first one being shifted back by 2 units. And when we look at x squared, then we see again the first term, second term is shifted back by 2 units, and the third term is again shifted back by 2 units. So it's shifted back twice, 2 number of times. And oh, dear me. And we see the same pattern over here as well. The first term is the first term, and the subsequent terms are the first term with the argument being shifted back by 2 units. So this is a sum from k equals 0 to n of the first term is always e to the ni alpha, but this argument is going to be shifted back 2ik alpha times. And this is quite beautiful because we see that the first term, the first exponential function, is in fact independent of the index variable k. So we have e to the ni alpha times the sum over k from 0 to n of e to the negative 2ik alpha, which is wonderful because this is another geometric series. We can expand this as, let's see, we have the first term being 1 times 1 minus the common ratio, which is e to the 2I alpha, negative 2I alpha, that is, time to the, it's the common ratio to the number of terms, and the number of terms here would be n plus 1. So this is in fact e to the negative 2n plus 1 I alpha, and in the denominator, we have 1 minus the common ratio, e to the negative 2I alpha. So far, so good, and we can actually make this a lot nicer if we expand using e to the I alpha. So we have e to the I alpha upstairs and downstairs. We have 1 minus e to the negative 2n plus 1 I alpha, divided by 1 minus e to the negative 2I alpha. And carrying out the multiplications, we have e to the n plus 1 I alpha minus e to the, there are two of them over here with a negative sign, so we're left with 1 negative n plus 1 I alpha. And down here we have e to the I alpha minus e to the negative I alpha. And again, some beautiful complex analysis, because if we just divide upstairs and downstairs by 2, we get the sine function. So we have sine of n plus 1 alpha divided by sine of alpha, which is awesome. Now that we have this infinite series, it should be smooth sailing from here. Well, yes. And no. The target integral I of alpha equaled the integral from 0 to 1 of log negative log x, terribly sorry about that, times this very function for which we do have a series expansion. That is the sum over n from 0 to infinity of negative 1 to the n times sine of n plus 1 alpha divided by sine alpha x to the n dx. Now switching up the order of the operators and noticing that 1 by sine alpha is in fact independent of both the index variable n as well as the variable of integration, that's x. So we have 1 by sine n times the sum over n, terribly sorry about that, of negative 1 to the n times sine of n plus 1 alpha times the integral from 0 to 1 of x to the n times log negative log x dx. And now we need to calculate this integral that I'll call I sub n, and we can do so very quickly. We have I sub n being the integral from 0 to 1, x to the n log negative log x. So it looks like a substitution here is quite obvious. We're going to let negative log x equal u, which implies that x here equals x here equals e to the negative u. And this further implies that dx is in fact negative e to the negative u du. And what about the limits of integration? Well, as x tends to 1, we have u going to 0, and as x approaches 0, we have u going to positive infinity. So I sub n equals the integral from infinity to 0 of e to the negative n times u times log of u. We have e to the negative u du with a negative sign, and we fix this as the integral from 0 to infinity e to the negative n plus 1 u times log u du. We immediately recognize this as a Laplace transform. It is in fact the Laplace transform of log u as a function of s, where s here in this case equals n plus 1. And the Laplace transform of log u as a function of s actually equals negative of the Euler-Mascheroni constant plus log s divided by s. So this implies that the target integral I sub 1 equals negative Euler-Mascheroni plus log n plus 1 divided by n plus 1. So now that we have this result, we can celebrate at the fact that we have quite a bit more work to do. Yeah. So we have the target integral I of alpha equal to negative 1 by sine alpha times a bunch of stuff. We have first up the sum from n equals 0 to infinity of negative 1 to the n times sine of n plus 1 alpha divided by n plus 1 times the Euler-Mascheroni constant. So I need some space for that. There we go, Euler-Mascheroni, and that looked a bit weird. Still looks weird, but slightly better. Then I'll just give myself some more writing space for the other infinite series, and that is the sum, terribly sorry about that, the sum over n from 0 to infinity of negative 1 to the n times, again, sine of n plus 1 alpha divided by n plus 1, but this time times the logarithm of n plus 1. Okay, cool. That is That's quite nice. I mean, it doesn't look too bad. Okay, I admit it looks horrible. I hope you guys are still alive. I mean, you guys are okay, right? Comment down something to let me know. The first sum over here is actually quite nice. This really is nice. I mean, this is just a Fourier series expansion that I'll make evident by performing the transformation, letting n plus 1 equal to k. So we have the sum over k from 1 to infinity of negative 1 to the k minus 1 of sine of k alpha divided by k. And this is just the Fourier series expansion for the function f of x equal to x by 2, or in our case, f of alpha equal to alpha by 2, which is pretty easy to verify. Now, what about the other infinite series that I'm going to call S? Well, to evaluate this legendary-looking series, we're going to need a legendary expansion, and that is the Kummer series for log gamma x, which is absolutely terrible. I can't even remember it, so I'm just going to refer each and every step as per my notes. So we have 1/2 minus x times the Euler-Mascheroni constant plus log 2. Then we have a plus 1 minus x times log pi, which does look pretty cool indeed. And we have a negative sign minus 1/2 log sine pi x, correct? Yeah, that's about right. And we have the star of our show, 1 by pi times the sum over k from 2 to infinity of log k times sine of 2k pi x divided by k. And it is this term that we need to transform into our legendary looking sum S. So first things first, let me introduce a shift in the index variable, but we're starting off at n equals 0, and for that term we have log 1, which is 1. So we start our sum at n equals 1 instead of n equals 0, and then under the transformation, letting n plus 1 equal to k, we would have the sum over k from 2 to infinity of negative 1 to the k minus 1 of sine of k alpha divided by k times log k. Now, of course, notice that the problem is we need an alternating term, and that is absent from here. And also, there's a difference in the arguments of the sine function. But again, that is not really an issue because we can choose the argument x here so that our needs are actually satisfied. What I'm talking about is letting 2 pi x, we need the condition of 2 pi x equal to pi minus alpha. Reason for that being that if we have a pi term, we could introduce an alternating term by virtue of the sine of a minus b or a plus b, that kind of trigonometric formula. Let me explain what I mean. So if this is the case, then we actually need x equal to 1/2 minus alpha divided by 2 pi. And how exactly does that help us? Well, we have sine of 2k pi, terribly sorry about that, 2k pi x now equal to sine of k pi minus k times alpha. And we did need a k times alpha term, so that's quite nice. So we have sine k pi times cosine k alpha minus cosine k pi times sine k alpha. This thing is, of course, 0, and cosine of k times pi is negative 1 to the k. So this thing equals negative 1. Wait, it's minus negative 1 to the k, so that would actually be negative 1 to the k minus 1 or plus 1 means the same thing, of sine of k times alpha, which is really cool. But what about the other terms in the Kummer series that I should copy down? And I'm just going to copy the whole thing. And there we go. Knowing that our value of x is in fact, again, I'm going to copy this down as well, just to make sure I don't mess anything up. Our value of x is in fact 1/2 minus alpha by 2. So we have 1/2 minus x being equal to 1/2 minus 1/2 plus alpha by 2 pi. We have some cancellation, so the first term is alpha by 2 pi. It looks pretty sweet. Then we got 1 minus x. 1 minus x is just going to be 1 minus 1/2 plus alpha by 2 pi, which is, of course, 1/2 plus alpha by 2 pi. Suddenly I'm good at math. Then we have log sine pi x. This is going to be interesting. Log sine pi x. This would be log sine of what exactly? We got pi by 2 minus alpha by 2. So we have a phase shift that takes it into a cosine. So we have log cosine alpha by 2, which is, again, pretty sweet looking. And those are the 3 terms that we needed. Okay, cool. So this implies that we have log gamma, what exactly? Log gamma x, and x is 1/2 minus alpha by 2 pi. This is the hardest bit of the video, just compiling results. So first up, we have alpha by 2 pi times Euler-Mascheroni plus log 2. Then we have a plus sign. Then we have 1/2 plus alpha by 2 pi times log pi. Then we got a negative 1/2 times log cosine alpha by 2. And finally, we have plus 1 over pi times the sum over, wait, let me think this through. We have the sum over k, log k, sine of 2k pi x. And all of that 2k pi x stuff was actually equal to this stuff. Again, quite nice. And then we have the log term that wasn't even copied. Oh, wait, the log term is up there. Sorry. This is a lot of work. So we got the sum over k from 2 to infinity, negative 1 to the k minus 1 times sine of k times alpha divided by k times the logarithm of k. Okay, cool. So on the right-hand side, we have exactly the sum we needed. So that means we need to throw everything else on the left-hand side and expand by pi, which is exactly what I did here. Notice also I have a log 2 pi term that comes from this log 2 and this log pi term being added up to give log 2 pi. And of course, we have the common coefficient of alpha by 2. Okay, cool. Well, it was alpha by 2 pi, then I expanded it by pi. Yeah, I remember now. Sorry, math glitch. Anyway, so now it's time to piece everything together. This sum evaluated out to gamma times alpha by 2, and we have exactly the same term over here, but with a negative sign. So we cancel it out, and we're left with I of alpha being negative 1 by sine alpha times a lot of stuff that is absolutely insane. We have pi times log gamma 1/2 minus alpha by 2 pi. We have minus pi by 2 log pi. Then we have minus alpha by 2 log 2 pi. Finally, we have pi by 2 times log cosine alpha by 2. And this is absolutely beautiful, but we can do slightly better here. We can factor out a pi and notice that we have logarithms everywhere. We have negative pi by sine alpha times log gamma 1/2 minus alpha by 2 pi minus 1/2 of log pi, so that's log root pi, minus log 2 pi to the alpha by 2 pi plus log square root cosine alpha by 2. This is awesome. Now using the properties of the logarithm, we can combine everything, but let me distribute this minus sign along with it instead of reciprocating at the end. So we have pi divided by sine alpha times the logarithm of a lot of stuff. We have 2 pi to the alpha divided by 2 pi times root pi divided by cosine of alpha by 2 square root cosine alpha by 2, that is, and we have gamma 1/2 minus alpha by 2 pi. And yes, this closed form is absolutely gorgeous. It is amazing. It is symbolic of the madness that preceded it, but you know how much I love the reflection formula, and it plays in so well here. Recall that if we have gamma z times gamma 1 minus z, that equals pi divided by sine of pi times z. So in our case, we would have z equal to 1/2 minus alpha by 2 pi. So that would give us gamma 1/2 minus alpha by 2 pi times gamma 1/2 plus alpha by 2 pi equal to pi divided by the sine of pi by 2 minus alpha by 2, which we recognize as a phase shift that just gives us pi divided by cosine alpha by 2. And that's exactly what we have here. We have that in the square root, which means we can make use of this result. And let me just copy this down. So we have the result I of alpha, and we have pi divided by sine of alpha times the logarithm of 2 pi to the alpha by 2 pi divided by gamma 1/2 minus alpha by 2 pi times the square root of gamma 1/2 minus, terribly sorry about that, 1/2 minus alpha by 2 pi times gamma 1/2 plus alpha by 2 pi. So we have one term upstairs in the square root and the term itself downstairs. So we have pi divided by sine of alpha times the logarithm of 2 pi to the alpha by 2 pi. Terribly sorry about that. And what does that mean we have left? Well, we're just left with the square root of gamma 1/2 plus alpha by 2 pi divided by gamma 1/2 minus alpha by 2 pi, which looks absolutely insane, and we could simplify it just a little bit more. Notice that we have, wait, I think I've been making a notational error that's pretty bad on my part. So yeah, notice for this 2 pi term, we actually got it from over here. So the coefficient turns into the exponent for the whole argument, correct? Whereas over here, it looks like I'm applying it only to the pi, although 2 pi is itself just one number. So I guess it's not that wrong, but yeah, bad notation. Anyway, so this is just something that's going to be carried forward. There we go. So we have the whole thing to the alpha by 2 pi. In other words, we have the whole thing to the alpha by pi to the 1/2, implying that the integral function I of alpha sorts out to pi divided by sine alpha times the logarithm of the square root. So we'll again make use of the properties of the logarithm. We'll write it over here, and we have log 2 pi to the alpha by pi times gamma 1/2 plus alpha by 2 pi divided by gamma 1/2 minus alpha by 2 pi. Wow, that was insane. I absolutely loved the solution development. Like, comment, share the video across YouTube, across the internet, across the world. Everyone should have a look at this absolutely gorgeous closed form for this monster integral. Be sure to like and subscribe, and in case you like the effort I'm putting into my work, consider supporting me on Patreon. Thank you. See you next time.